Okay, now we're going to look at another method for calculating the areas of the volumes of solids that have been revolved about a axis. We've looked at the disc and washer method, but sometimes it is difficult to solve for the variable that we need it to be in. You saw how when we rotated something about a vertical axis, we needed it in terms of y. Sometimes it's difficult to solve for y, or vice versa. So there's another method we can use called cylindrical shells, which will provide the volume for us. And so it is based on cylinders. So this is the image that I want to give you, basically. If we have some solid, we can kind of cut it into, not slices, but cylindrical shells. So the image, and maybe this will make more sense as we get into it, these are little Russian dolls, measuring cups from dolls. But these are, do you see how these are little cylinders? It's a cylinder, inside a cylinder, inside a cylinder. And so we stack these little shells together. This is one way of looking at this. Another image I have is just paper towel rolls and things. Here's a little cylinder inside of another bigger cylinder, inside of a bigger cylinder. And so when you can calculate an area by approximating them by cylinders, and you'll stack them inside each other. Of course, the thickness, you'll have a lot more. These are just the three I could find. They'll be closer together. The thickness will be dx. They'll be very small. So again, the more cylinders you use, the more accurate it will be. So if you're using an infinite amount of cylinders, you're going to get an accurate volume. So here is a picture of a cylinder. In fact, let me just take this one. Here's a cylinder. I'm gonna cut this open. And you'll see that when we cut open the cylinder, we get a rectangle. And so that's how we're going to calculate the area of the volume of a cylinder is the area times the thickness. So the area of this is simply going to be length times width. But if you look here, let's look here at the length of this. That is the same as the circumference of this. So when we calculate the area of a cylinder, if you were to cut it open like I just did, okay, you lay it open, you're going to get a rectangle. And we unroll it. So this length right here is the circumference. So this is 2 pi r. And then by this times, this is length times width, and so, or base times height, this is going to be how high, the height of that cylinder. So this is the area, okay, of the cylindrical shell. Now, times the thickness, because these all have like they're all a little thickness on there, right? The thickness, but that is our dx. So basically, it's the same formula. We're going to integrate from across an x distance or across a y distance, and this is the way this is written as an x distance. And so it's the area. In the past, it was the area of a disc or a washer, but now we're doing the area of a cylindrical shell, which will be 2 pi r times h times the thickness. Okay, so we're going to have to convert these in terms of x's and y's, but this is the basic principle. So let's just do an example and you'll see how these work. Again, in the book they have pictures of cylindrical shells so you can see how those fit inside of each other. Example 1, find the volume of a solid obtained by rotating y is equal to 2x squared minus x cubed, and y is 0, okay, about the y-axis. Okay, so it is good to draw a sketch each of these. So here we go. y is equal to 2x squared minus x cubed. This is a cubic function, okay, and it's a negative cubic, so it would be like this. It's going to look kind of like this. Let's see. You can factor out to get an idea of this. You can put this in a calculator. You can just point plot. I'm going to think about this as a polynomial function. I'm going to factor out a negative x from this, giving me, or maybe just factor out an x. That gives me 2x minus x squared. Oh, let me factor out an x squared. It gives me 2 minus x. Okay. Why am I doing that? Because I want to find the zeros of this function. There's a 0 at x is 0, and there's a 0 at x is 2. Okay. All right. This is where it's crossing the x-axis. And I'm interested in that because y is 0. And then what's happening in between here? If I want to plug in 1, 2 times 1 is 2 minus 1. I'm up here at 1. Okay, so it's doing some kind of polynomial thing up here. Maybe it does that. I don't know what this does exactly. So I'm going to say it does that. And then I need to rotate this about the y-axis. About the y-axis. So that means whatever it's doing in here, I think it looks like this. This is my area I got to calculate. So this is -2, and this is -1, and this is 0, and this is 1, and this is 2. So it's rotating here. So if we rotated the solids, we could see that. Now, you can see that this would look like, right, a washer. You'd have a hole in the middle. You can see this. It looks like a bunt pan. Do you know what a bunt pan is? Let me go grab one just a second.